So Dr. Nieto in the Department of Mechanical and Aerospace Engineering at the Naval Postgraduate School. Before joining NPS, Dr. Nieto was postdoctoral fellow at Army Research Lab. Right. He has served as a reviewer for more than 40 international journals. He has more than 50 technical articles in his research. He received more than 1,900 citations for that. And he has been awarded Office of Naval Research prestigious Young Investigator Program. So yeah, and Dr. Nieto will be talking today about designing materials using additive manufacturing, using additive processing. All right, so Dr. Nieto.
All right, good afternoon, everyone. Good morning. So my topic's on additive processing of materials, and I'm going to talk about nanoparticle reinforced coatings and composites. That's a lot of what my work focuses on. So just kind of a brief outline of where I'm going with this. First, I'm going to give you some of the motivation for why we use a lot of these nanoparticles, why we want to use these nanomaterials as reinforcement bases in the first place. And then most of my talk will actually focus on one specific system, on titanium CNT composites. And then towards the end, I'll just briefly mention some other work that we're doing on dual reinforced composites using actually another type of additive manufacturing technique. So just a little bit about myself. As I was introduced, I won't beleaguer it too much, but after finishing my grad studies at FIU and UC Davis, I actually did a postdoc at the Army Research Lab. So I kind of had a hand in doing metals, composites. Then when I went to the Army Research Lab, I was working mostly on high temperature materials, very application driven. So a lot of my work focuses on trying to develop materials for these extreme environments to enable new capabilities and to try to make materials that have some transition path forward that might be scalable, which is a lot of the reason why additive is so attractive. So I've been a faculty at NPS for just about 4 years now. These are my main research interests, but today I'm mostly going to be talking to you about the metal side here. But I also have some work, if you're interested in learning more about me, on 3D printing of polymer composites and on ultra high temperature ceramics. But I'm going to stick to mostly my metals work, which is mostly what I'm working on these days. So let me start off with composites. Composites are materials that use similar phases. Usually, you've got some sort of metallic or ceramic reinforcements embedded in a matrix. Classical composites start off with fibers for strengthening. You're trying to get better strength properties. And one of the main kind of principles of a composite is that you are trying to get the best of both worlds. So even though we add these ceramic fibers, for example, or even metallic fibers, we know ceramic are generally brittle. When we get very high aspect ratio fibers, it's actually a result just from beam theory, essentially independent of microstructure, that as you decrease your fiber size, essentially as you decrease the radius of the fiber, in this case from the beam theory, a beam, you actually get a much more flexible structure. So you can actually get very flexible ceramic structures by actually just decreasing the size. So when we deal with kind of classical carbon fibers, you see this relationship that as the size decreases, your actual strength increases quite a bit. So that's kind of just a 101 on why do we have a desire to make reinforcement particles smaller. You intrinsically get both better strength and the flexibility that you need in a composite. So carbon nanotubes actually presented a perfect opportunity to take this concept essentially to one extreme, right? We know that carbon fibers are very fine. So now let's look at carbon nanotubes. Not only are they nanometric, but now you're actually dealing with a very favorable form of carbon, sp2 bonded carbon, very strong, very stable. And for composites, we're actually mostly interested in multi-walled carbon nanotubes. And this is a TM micrograph, of course, of a nanotube, a multi-walled carbon nanotube. You can see the individual layers here. You have maybe about 15 to 20 layers in this tube. The individual layers have the same properties as the nanotubes. We actually like using these nanotubes in composites for two main reasons. One is, unlike with polymers, that you can do a lot of polymer processing at even room temperature or slightly elevated temperature, but for metals, you're going at minimum to a few hundred degrees Celsius. And for ceramics, for the most part, you're going above 1,000 Celsius for processing them, right? So we're trying to process these materials with nanotubes at those very high temperatures. It's certainly not inevitable, but it occurs very often that you get some reaction, right? So with aluminum, steel, titanium, most of those materials will actually form a carbide spontaneously, at least spontaneously in terms of thermodynamics. So if you had a single wall nanotube, you would lose all your material right away. If we have a multi-wall nanotube, we can actually afford to have a few layers react and form an interface, and we can actually get desirable interfaces sometimes. If we have just a very small amount of carbide, that's actually a very good thing for load transfer. The nanotubes themselves have very good mechanical properties. They have good thermal properties. They're lightweight. So all things that we like in the in a composite. Another interesting aspect of the multi-wall carbon nanotubes is that you get this so-called telescoping, or sometimes we call it sword and sheath mechanism. And you can actually get the interwall sliding between them. That's especially useful for ceramics where you're trying to impart strain tolerance onto the ceramic. So you actually don't want the reinforcement to be the stiffest material possible. In metals, it's a little bit more in between polymers and ceramics. You do want high strength, but if you can have some damage tolerance, so for example, if you're just stretching this elastically at a certain strain, you would just rupture it. Now, if you can actually just essentially have them telescoping out, that gives you a little bit more room for strain. So very good for energy dissipating, strain energy. These are different nanostructures that I've worked with. These are all my images. We've become very interested in two-dimensional nanoparticles as well. Some of the same ideas apply. You've got a very high surface area phase, good for transferring load. You have very good in-plane mechanical properties. And just like in the case of the multi-wall carbon nanotubes, you develop some interesting mechanisms when you actually stack some of these layers. And usually, if you're talking about individual layers, let's say graphene, for example, you still want to have something no more than maybe 20 to 30 layers. If you start going beyond that, you start losing kind of the unique properties that occur at nanoscale and start going more like a piece of graphite, for example. At 100 layers, you're pretty much dealing with graphite. But when you're still at 10 to 20 layer range, you actually get these interesting deformation mechanisms. And you think of, you see graphite. Graphite is not the material we think of as being very ductile, right? Yet you see these platelets, you can see that they're deforming at 90-degree angles without fracturing. It's a very interesting process and property. These were actually just nanoplatelets alone without any composite. And you can see individual sheets bending. This is kind of the ideal behavior that we would want when reinforcing a ceramic, right? A hard, stiff material that's able to deform, that allows you to absorb strain energies that would otherwise go into fracture. And so that's kind of one of the reasons why these are really good candidate materials for using in composites. So what about the additive part? Additive is somewhat old technique, but it's received a lot of attention, mostly because of the practical ability to, hey, we can 3D print parts potentially on demand. The Department of Defense is really interested in it because you could potentially have one of these machines on a ship, and you could print the parts you need, or you could have it on a forward operating base on the other side of the world, and you can print the parts you need. So very practically very useful. Industry likes it because you can design something on your computer and you can go prototype it right away. But as a material scientist, I really like this technique because it allows us to essentially synthesize materials layer by layer. And we're talking about pretty fine layers, micron size. And there's definitely some challenges to it. You know, each layer is almost like a single welding processes. I'll talk about some of the challenges in the next slide, but to give you an idea, you know, you can change things in a single layer by how you're rastering the beam, the direction that you're rastering the beam, the different parameters associated with the beam, such as the speed, the power, the energy density. And then you can also change composition if you want, right? You are depositing layer by layer. You have the flexibility to change composition at a very small scale. So from a material science point, it's a really unique tool that allows us a lot of flexibility in design. And it's actually, it works perfectly with powder metallurgy. That's a lot of what I do. A lot of what I do is just pure powder metallurgy, working with metallic ceramic powders, modifying them for specific either applications, trying to get new compositions, distributions of size, morphology, and powder metallurgy by no means is a new field. It's a very old field, but it works perfectly with AM. This is an example of kind of a typical work plan that you could go through using powder metallurgy to actually get you know, novel composites or structures in bulk. You would essentially start with powder synthesis, and you can do it chemically, you can do it with ball milling techniques. There's all sorts of different ball milling techniques, high energy ball milling, cryo milling. We use mostly those three techniques in our lab, and depending on the nanomaterial we're using, there's different techniques that are better suited to it. Sometimes we may need to have extra steps, for example, with 3D printing. Sometimes you may need to sphericize a powder. Normally, we try to actually avoid those extra steps and just go directly from powder synthesis directly to additive processing. And mostly what I use are cold spray, which is more of a coatings technique layer by layer. And then selective laser melting is for actually 3D printing pretty complex structures of metals. And now that so this is definitely something that's to scale. So once you are done producing your powder, you can, in theory, produce very large structures for, of course, applications, but also for testing. So we can print tensile specimens. We can print, in theory, a large plate for, let's say, ballistic testing, for example. Normally, we actually do a lot of our basic characterization at a small scale, and usually the largest we go is to maybe tensile specimens. And this is an example actually of a cold spray coating. This is actually a coating that delaminated that was not doing well, and then after some straightforward heat treatments, the coating layer actually deforms alongside the coating material. So I'll just talk about ball milling a little bit more, because a lot of what we've done that kind of underpins the additive research is based on the milling. And when we're milling these composite powders, we're not really doing traditional milling where you'd normally be alloying something and you'd be trying to get high temperatures and you're trying to get doing different phases to disperse at the atomic scale or alloy at the atomic scale. Here, we're trying to break up powders, and I'll show you in a couple of slides that nanomaterial powders, if you're not familiar with them, usually you're buying them in an agglomerated form. So we have to break that up in the first place, and then we have to disperse them. And essentially, the more strain you impart on the system, the less time there is going to be to disperse it. And there's a balance between how much strain you impart in the system and how much potential damage you do to the nanoparticles, which you're trying to keep them in a pristine state. And depending on the technique, we can essentially use nanotubes, nanoplatelets, zero-dimensional particles. And we've actually done a lot on just focusing on metallic powders for AM in general, because before we even add the reinforcement, we need to make sure that the metallic powder is going to have some heat properties. Most of what I'm going to talk today is actually on 3D printing, which kind of has some of the most sensitive requirements for the powder. The powder has to be able to spread very nicely on its own, since it's gravity fed. So you can imagine that if you're starting with something very fine, let's say if you're just doing nanoparticles by themselves, that would be very sticky. You would never get a very nice flat bed. So using ball milling, we can control the morphology, and we can also control the hardness of those particles. And this short study basically gave us a blueprint of what could we do essentially with the high energy ball milling technique, but actually doing the inverse of that, using relatively low milling, where we're only going up to maybe 30 cycles, where one cycle is actually 2 minutes of actual milling and 5 minutes off. So this kind of gave us a blueprint of, what can we get away with milling without changing the morphology of the particulates that much. And you can see if we go to very high energy ball milling conditions, we just get platelets, and this would never actually flow. So these are actually some of the composite feedstock powders that we've made. And we've had a pretty good time with, making all sorts of different compositions and getting exactly what we want. These are some of my favorite images. So these are titanium spherical particulates, kind of what the company sells for the machines. And what we've done is we've essentially decorated them with oxide particles, in this case, tantalum oxide, pentoxide in this case. And you get very uniform distribution, right? You see essentially no agglomeration. So you're really trying to get two things. You're trying to get it on the surface of the particle, because by themselves, the particles are not going to flow. They're very fine, they're sticky. They're not going to form a uniform powder bed. So they need to be attached to the larger particle, essentially as a carrier. If you have a few loose ones, it's not a big deal, but you want them to be attached, and you don't want to change the shape of the particle. If you start getting platelets, then you have problems. And you can see here, this is the feedstock that I'm going to talk mostly about today, this titanium CNT. It's still mostly spherical, and it's covered with CNTs. And I have another slide there, and this image might be a little bit hard to see, but this is actually a platelet in between some of the particles. So I'm going to talk about this system specifically for most of the rest of the talk. We essentially 3D printed Ti-64 composites with CNT reinforcement. And the mechanical property reinforcement part is still very basic, but the processing to get there is quite interesting. So inherent challenges to both working with CNTs and selective laser melting. CNTs, when you buy them in bulk, so we're using industrial quantities, so we can get a kilogram of these CNTs, high quality CNTs, at least 95% purity, which is definitely important. I'll mention it later, for about $1,000 a kilogram of it. But they come in this agglomerated state. So one of the biggest challenges to using them in a composite is we need this to be dispersed. We want it to be uniformly dispersed, as opposed to essentially a connected network of fibers would be the ideal structure. As far as 3D printing goes, I mentioned earlier that each individual layer is very similar to just a single weld, and you actually get very high residual stresses. So that's kind of an interesting challenge to deal with. You can actually do interesting studies where you can actually 3D print material that if it's essentially under residual stresses, it's actually going to deform by itself. It's going to deform, and you can actually quantify the residual stress state right as soon as it's printed. And you can do some modeling, etc. If you do end up with CNT agglomerates in your final structure, so this is a TM image showing clusters of CNTs in your final metal matrix composite, you actually can lose a lot of the benefit of the CNTs. This cluster is not going to provide a lot of strengthening. In fact, just the opposite. Within the cluster, you may actually have enough porosity that they can serve as a defect site. So that's why you have to be, very careful when you're processing these materials. Dispersion and getting a good quality starting powder are quite essential to being able to get a useful end product. So the 3D printing itself comes with a lot of challenges when we start adding these different composite phases. So at left here, you actually see one of our earlier runs with the titanium powder with nano aluminum oxide. This was essentially our very first run. No optimization. We were essentially using the same parameters as Ti-64, and you see a lot of issues here. One, the powder bed was actually not spreading very nicely. The nanoparticles were causing some roughness, and essentially the powders were sticking together more. We also had not done any optimization of the power. We were using the standard power and energy density for Ti-64, and that was actually too high for working with the aluminum oxide, especially being nano. It was actually dissociating very quickly, we think. We don't have proof for that, but it was essentially dissociating, and we think it was, even though this is under inert atmosphere, we were getting these little combustion events that you see going on there. And this is clearly what it's supposed to look like. This is essentially a single layer of powder. This is our titanium CNT. These are large impact specimens that we printed. You see a uniform bed, and the laser is just printing or essentially solidifying the layer that you want. So it works very nicely in that case. So these are kind of some of the specifics as to how we made the powder. This is the kind of CNT that we were using, and we tried different milling techniques. We tried using solution ball milling where you have a lubricant, but we actually came up with a processing routine. So this is more kind of definitely on the engineering side of it. We have guiding principles, but we came up with a solution where our powder is quite good and we can actually reuse it. We can actually reuse it several times and still be able to print with it. When I say our powder is very good, this is one of the objectives we were trying to achieve. We were trying to get those nanotubes I showed earlier kind of bundled up. They start very bundled up. Now here you've got this entire surface of the titanium particle. So these are essentially the background of this is just the pure Ti-64 powder, and you see small nanotubes coming out of it, pretty uniformly dispersed. Really no signs of agglomeration here. So goal number one accomplished, right? CNTs are uniformly dispersed. Second goal, I said we want to keep the shape very close to spherical. As soon as you lose that spherical nature, it becomes very hard for it to flow very nicely. Spheres are kind of the easiest material to flow. And so you see that here for the most part. We have every now and then a particle that has been a little bit flattened, but with this amount, it's perfectly fine and it flows very nicely. So we could, we needed to go through all of that powder processing just to have something that we can actually print, right? It's not a trivial process where you could just mix them. If you don't mix it right, you're going to have problems from the very beginning, kind of like I showed with the aluminum oxide. These are some of the main parameters that people use when modifying the 3D printer. These are the main ones associated really with the laser. There's other minor parameters such as the argon flow, the vacuum before it, the planarity of the substrate. But essentially, we look at the energy density, the energy that's being input into your metal to essentially form a melt pool. And the melt pool essentially is what's driving the solidification that eventually gives you a part. So we've got the power of the laser, the actual scan speed of the laser. And if you're familiar with welding, you know that how fast you scan across it can really impact your residual stresses. And then the actual layer thickness of the powder. That's set by the machine in terms of how thick you want your layer to be, which is basically just a blade coming across your powder. So in this first study, we're actually really interested in just seeing how does the presence of CNTs influence the effect of these variables, with the energy density being our primary interest. So we essentially, this nomenclature here, E60 refers to the actual energy density. And then the second one refers to the power. So sometimes we, for example, we might get an energy density of 60, but we can use a range of powers and we can compensate with the velocity. So if we're using a higher power, then we have to stay there for a shorter time or essentially move it quicker. So our first work kind of focused on a very low, relatively low energy density of 60 and a higher one of 417. To give you an idea, the base energy density for Ti-64 that the company essentially provides that they've worked on is 66. And you get different pros and cons at each end of the spectrum. At the low energies, if you go too low, you could risk not having actual sufficient melting, right? We're talking about refractory alloys and It's going to be a different case if it's titanium or if it's tungsten, which we can't print, by the way, or aluminum. Aluminum is very hard, more because of its properties, its optical properties. And if you, of course, if you start off with something that's not really molten enough, then you're not going to have a good solidification process. You might actually do more sintering it. Some of the older processes are called selective laser sintering, where that's the idea. You're sintering it together as opposed to melting it. So you do need a kind of minimum floor in terms of the energy you're imparting. So you might wonder, well, why don't we just go to very high energies and have it, very molten, and you completely eliminate that problem. In terms of our nanotubes, we were a little bit worried that at very high energies, we're going to increase reactivity. And actually, one Chinese group beat us by maybe 6 months or so publishing this work. And in their composites, actually, and I'll talk about it in a couple of slides, but they essentially destroy all of their CNTs in the first place. But aside from potential damage or reactivity with the CNTs, you actually lose resolution at this high energy. When you have such a dynamic melt pool, you're inputting so much energy into the melt pool that it becomes very turbulent, very unstable, and you're not able to get very nice, precise surfaces. And my very last slide of this topic will have some images of parts we printed. But you do lose resolution, which practically is a problem. So these are kind of the microstructures that we obtained. These are just optical micrographs for now. Just wanted to give you a general idea. We get pretty good density in the products. And one of the biggest differences that you can notice as a function of energy, you actually get more porosity at the higher energy density. And there's different sources of porosity. I'll talk about it in the next slide. But the biggest difference, if you just compare between Ti-64 and Ti-CNT, is you actually get much finer structures. And the structure of a Ti-64, if you're not familiar with it, it's mostly an alpha beta structure. So you've got these alpha needles that are HCP, and then you've got the beta phase that's BCC, and that's the more ductile phase. So it essentially has a good combination of ductility and strength. But the Ti-CNT structure under identical conditions, just the addition of 1 volume percent CNT, that's actually all we've gone to in what I'm presenting here, gives you a much finer array of needles. And then this is the porosity that you get. There's different sources of porosity. If you have very spherical porosity, a lot of that actually just comes from the starting powder. Especially when we mill it, we can get entrapped air. And that's not terribly problematic. It's also very closed, so it doesn't form an interconnected channel. At higher energy density, not only do we get more porosity, but a lot of porosity starts becoming asymmetrical. And that's because some of it is actually due to evaporation occurring, because the melt pool is very unstable. You have a very high temperature, and then you also have splashing. You actually have a melt pool that's so turbulent that you get splashing, and that can cause inclusions, and that's some of the source of porosity. So yes, as a function of energy, we get more porosity, and we also get slightly more porosity when we add the CNTs. And we think that's mostly due to, in the lower energy case, most of the milling. The milling is a dynamic process, and you're essentially, impacting particles one another, and you may get entrapped air during those impacts. And at the higher energy, the CNTs are very conductive phase. They are very high thermal conductivity. For this and for a couple of other reasons, we think that they are increasing the actual temperatures that you're seeing. So here you have a SCM of some of the types of porosity that we encountered in the sample. And this is not our paper. This is a paper where they essentially looked at the laser. They essentially had high-speed cameras, and they're imaging the laser interacting with the melt pool, and they can see the sparking. And the sparking is actually not sparking, it's actually splashes of metal coming out, which leads to some of these problems. This is the actual data for our study, where we essentially, as a function of energy density, I'm showing you the porosity. And you can see that for the most part, the composite does have a lower, has a lower porosity. But what you also kind of see is that it's actually a lot more sensitive to the higher energy densities. It drops much quicker than the actual Ti64, which is going to influence the hardness that I'll show in a couple slides. This is SEM of the microstructure. Here you get a much better view of just how much finer the structure is with CNTs. The needle structures are much finer at equivalent energies. And then also as you go to higher energy, in both cases, it becomes finer. You'll also notice here these particulates that evolve in the Ti-CNT case. And this only occurs in the Ti-CNT. So we have a pretty good intuition that these are actually carbides. And in fact, X-ray diffraction did show that we were forming some sub-stoichiometric titanium carbide, which is commonly the type of carbide that you get in selective laser melting because your kinetics are so fast that not all of the carbon interstitials are able to be filled, and you get this sub-stoichiometric phase. So we knew we had titanium carbide, which was certainly not the goal, but you'll see later that we did retain some of our CNTs. This was our main result that we got in terms of mechanical testing so far that I have here. You get a significant increase in hardness across the entire spectrum of energy densities. And keep in mind that that's despite having much higher porosity. So our strengthening mechanisms are making up for that porosity. And you'll also see that, so you get the largest strengthening effect here at about 60. You'll also notice that the trend is different. For the composite, strength actually goes down as a function of energy density. And for the Ti-64, it actually goes up. So this is kind of, what we think is happening to the carbides specifically. We actually see them at higher energy densities throughout the structure, these very small carbide particles. We also saw intact CNTs. So these are essentially CNTs bridging a very small pore in the sample. And as far as we know, we're the only study so far. There's one published this year that I think on stainless steel got it done. But in terms of titanium, the only studies that have tried this have essentially lost all of their carbon nanotubes, and they're left with nothing but carbides. We actually have some nanotubes remaining, which is what we wanted in the first place. We wanted more of a fiber type reinforcement. And you also see them embedded here. These are long nanotubes that are going in and out of the surface of the structure. You only see this in the composite samples. And what happens to some of these nanotubes is they do react with the surrounding matrix, and they start forming these elongated carbides. We think this is essentially representing the transition between the nanotube and then reacting with its surrounding to form kind of these almost lines, right? Almost these lines of linear carbides, which is not a common morphology for titanium carbides to form this kind of linear structure. We're pretty confident that this is directly emanating from the presence of CNTs, and these carbides will then essentially break down into the individual little platelets here that you see, in part because when you melt each layer, subsequent layers, you're actually remelting 3 or 4 layers underneath. So you're actually remelting the material, causing a turbulent melt pool that can actually break these apart as they form. So in these composites, we have all three. We've got these single carbides, we've got these linear chains, and then we've got individual CNTs, and we're able to make these 3D printed structures, very complex shaped. You could not really, so these are all titanium CNT, and you can't really attain a lot of these intricate shapes with just about any other processing method. And some of our future work here is related to making larger specimens and trying to look at deformation within the SEM, try to prove some of these mechanisms, and doing some TM to look at the carbides and see if they're piling up dislocations or not. I want to switch gears slightly to talk about a new area that we're kind of starting. which goes with the theme of additive manufacturing and nanocomposites. And that's actually to make hybrid coatings with dual reinforcements so that we can actually repair metallic materials. So in this case, the additive nature is actually to repair a structure that has been damaged. Might be a crack, might be an impact. We want to fill that. And the dual reinforcement part is a topic that I've really become interested in because we know with alloys, we use different alloying elements all the time, right? We use them for different purposes. We haven't done that a lot for composites using nanomaterials. We've used individual nanoplatelets or nanotubes, but there's actually a lot of interesting synergistic effects that you can get with them. So let me just introduce the cold spray process. So this is the additive technique that we're using here. We start with very similar powders as I discussed earlier. This technique is actually a little bit more robust in that you can get away with not having perfectly spherical powders. You can have very elongated particles. You are actually driving them with a pressurized gas. So that actually helps them flow as opposed to the 3D printing system that is essentially gravity fed. But this technique, basically, it's called cold spray because it's cold relative to other thermal spray techniques like plasma spray or HVOF, cold relative to most traditional metallurgical processing. And in this case, we're actually not trying to melt the metals. It's a solid state processing route, which in itself is quite interesting. And what you do is you take it through a heated gas. The newer systems are actually going all the way to 900 C. Traditionally, most cold spray was done for aluminum, and for those systems, you really just have to go to 400 C gas temperature. Your particles spend very little time in that gas because this is a converging, diverging nozzle that actually makes the flow supersonic. So you're spending on the order of maybe microseconds. You're just trying to heat the gas up enough that it softens. It softens because you are essentially going to take those particles and you're going to blast them onto the surface. And when you blast them onto this surface and they're warm, so they're soft, they actually go from being spherical particles into being essentially splats or essentially lamella. And they form this deposit layer by layer, where each layer is essentially made of several powders that have essentially been impacted onto that substrate. And we do know that when we incorporate ceramic particulates into the process, we can improve the deposition efficiency, the hardness, the wear resistance. So what we're trying to do is we're really trying to get, and this is kind of a schematic of what the process, a simulation of what the process looks like. Your particles impact the substrate, and there's actually some mixing that goes on there with the substrate, which is actually quite interesting. And we're making use of this approach when we make composites designed to get better adhesion, for example. One of the things we're doing is we decorate these particles with nanotubes, and now when they impact the surface, now you're going to have nanotubes essentially bridging those interfaces that you see there, and we actually can get better adhesion there. To kind of back up a little bit, why cold spray? Other techniques that are used for repair are inherently high temperature. With competitors being mostly thermal spray, which is analogous idea, except you're not using a cold gas, you're actually using a combusted gas or even a plasma flame, which is going to actually melt your particles. And those systems are designed to melt it. So this is an HVO system. You're shooting particles into this combustion flame. And yeah, you can use it to coat very large pieces. So it's a very scalable piece. And then the other more classical technique is welding. You weld something, and if you weld at very high temperatures, you can actually cause severe corrosion problems. So in this case here, you actually have a stainless steel that has been sensitized. And when you weld something, you can sensitize something very easily. And basically what you're getting is you're getting precipitation of carbides that deplete the grains of the chromium. The chromium that makes it, you must all know, especially if you've taken corrosion class, that we add chromium to essentially form a passive chromium oxide layer. That is what makes stainless steel stainless. And if you lose that, then you essentially form a very localized anode cathode. And these are the types of problems that we can avoid with cold spray. We can fill metals, we can join metals without having to heat the substrate. Certainly not to hundreds of degrees, but even your substrate temperature in cold spray is going to be less than 100 C. So in that case, the substrate certainly is cold. So we're trying to make composites that have use of dual nanoparticles so that we can get both strengthening, but also try to get some useful properties. And what I'm going to show briefly here, we used boron nitride nanoplatelets because it's a large surface area, ceramic phase, relative insulator. And so the idea is that we were actually trying to incorporate this phase to decrease the conductivity of the coating itself, so we could try to essentially decrease the corrosion process, try to short circuit that corrosion process a little bit. And we got some interesting results. These are the cold spray composite coatings. This was done using a high pressure system. This is kind of the classical structure you get with cold spray. All of these individual features that you see here are essentially particles that have been flattened apart. They've eventually been flattened. And if you look at this this indent profile here, or SEM images of it, on the left is the composite. So you can see at equivalent load, you have a smaller indent, higher hardness. But then if you look at the morphology, you actually see some pileup here, or buildup of material in the circle area. And that represents that you have some plasticity in the material, which you don't really have in the starting cold spray deposit. And so we did the hardness testing. It showed improvement. We did corrosion testing using a sulfite chamber, and we haven't done too much of the polarization type experiments yet. But the Navy is very interested in sulfite chamber testing because it's one of the most realistic environments, short of actually putting something out on a boat. So we ran these tests for 2,000 hours doing characterization before, also 1,000 hours. We do some preliminary testing at 500 hours. And when you look at the cross sections, the weight gains were actually slightly lower at initial times, then they essentially even out. But when you look at the cross sections, it's really when you get some striking results. You see here, this is the coating material on top is this kind of slightly darker phase. And this is the pure aluminum coating. And then this is the coating with actually both boron carbide. It was there mostly for strengthening and also to help with the dispersion of the BNNP. That was one of the synergisms that we were trying to get. We were trying to get the boron carbide to actually lay in between the platelets and actually help keep them from agglomerating together. You can see that at this interface, what's going on in this micrograph is you actually have galvanic corrosion occurring between the coating layer and the substrate. We were very surprised that this happened. Our substrate was 6061, and our coating was just pure aluminum or commercially pure aluminum. And we were surprised that that was a sufficient galvanic mismatch to get. And this is something that really wasn't seen before because most corrosion was occurred at short enough intervals that you didn't see this. But at 2,000 hours, you did start getting galvanic corrosion. And once it started, it accelerated. You don't see that in the composite. In the composite, we think that the BNP and B4C to some extent, they're able to at least reduce some of this current, essentially that's the driving mechanism. One of the driving mechanisms for corrosion, we're slowing down the current. And we think that's why we didn't get that in the composite. And then this is just essentially the interface of the B4C coating. The B4C alone was not giving us the same effect. So we do think that it was the platelet morphology that was letting us form, even at very low compositions, a good percolating network of that. And kind of big picture, just to wrap up, we know that cold spray is also a very useful technique where it's a portable technique. It can be used at the site of need to repair these structures. And what we're trying to do is we're trying to essentially come up with the next generation of materials and demonstrate it in a scalable fashion. So when we make this new aluminum boron nitride composite, we can show, hey, it has useful properties. And by the way, we're able to make this material in the same exact ways that we envision the end use application, which is by cold spray. So we've actually patented some of these compositions, and we have this path forward for how to transition the technology, because we are using the same processing route that we actually envision for the application. So I've given just kind of an overview of some of these projects. All of this is published work. So I'd be happy to pass along any presentation, any papers if anyone wants more details on any of this. And as always, I just like to thank the sponsors. Mostly ONR has funded this work, but also some funding directly with the shipyards who are very interested in this, as well as related work with the Army Research Lab and the CERTA program. So that's all I have. So thank you very much for your attention, and I welcome any questions.
Hey. A lot of useful information. So, questions?
It was a nice work.
Thank you.
Thinking from the perspective of a corrosion scientist, I'm curious, what will be the corrosion performance of this metal matrix composites you introduced in the initial slides?
The titanium CNC ones? Maybe your colleague could tell you a little bit about those, but we haven't really looked at them. We were not doing those a lot for corrosion application. Actually, just the opposite. We're actually targeting those for some space applications where we wouldn't have a lot of corrosion issues because they're very lightweight, and CNTs have good irradiation properties. But normally, so there's other literature on not 3D printed. Well, I think there's some now, but normally CNTs don't do you a lot of favors for corrosion. There's an inherent galvanic mismatch there, and you start getting these micro galvanic couples. Even under short-term corrosion testing, you start seeing the effects of that crevice corrosion, which is actually why for the cold spray work, we didn't go with carbon nanotubes, we went with boron nitride nanotubes because at least they're electrically non-conductive or low conductivity, nothing is truly non-conductive. So that's one of the reasons that we tried with that.
In the case of boron nitride, did you look at the interface? The interface here?
No, we're actually at MPS, we're just in the process of installing a Helios where we can make fit samples, but no, we haven't looked at the interfaces in any detail beyond what you could see in an SEM, which is not much. But, with aluminum and boron nitride, the few studies in the literature don't show a lot of reactivity between them, unlike with carbon nanotubes that form carbides. So we should get mostly just physical bonding and mechanical adhesion.
I was wondering if there's some oxide, boron oxide.
Oh, boron oxide. I wouldn't expect it just because of the very low processing temperature. I know borea forms very low temperature, but our maximum temperature in that case was actually for the aluminum system was 350. So I don't think we're oxidizing the boron there.
Yeah. You talked about the need for cold spray in shipyards and how it's, I guess, more convenient for a certain level of access to repairing parts. I'm curious about the sort of the way that the cold spray happens on a substrate and what the material science connection might be to corrosion resistance versus another type of coating. Is there any link to, is it you're doing cold spray purely because it's convenient, or is there actually an extra benefit to the cold spray over another coating?
So in terms of corrosion, I have to think about it. I'm going to try to think about it now. But in terms of adhesion, you can get really good adhesion when you spray like materials. So for example, when we sprayed aluminum on even just aluminum 6061, it's essentially intermixing during that mechanical deformation. It's very difficult to even make up the interface. The only reason we're able to find the interface in that case is because there's precipitates in the 6061. Otherwise, it's very difficult to form to see the mechanisms. You get very good adhesion. You are severely plastically deforming the material. So you actually get a very hard material just intrinsically with cold spray. And from a processing standpoint, it's actually quite useful to start with something that's very hard, because then you can bring it back as needed with a given anneal. In terms of the biggest advantage is the low temperature processing. That's one of the biggest kind of materials reasons. In terms of corrosion, I think one advantage, and it would apply to limited systems, but is the avoidance of second phase formation. So for example, in the case of steels, if you don't heat it very carefully, you have to do very precise welding to avoid precipitating out those carbides. That low temperature processing allows you to avoid phase transformations. And from a kind of composite standpoint, kind of what I do, that allows us to process things like carbon nanotubes, nanoparticles without worrying about them growing or dissociating because it is a low temperature processing grid.
More questions?
I have a couple questions that might lead to one more central question. The tie 6 core composites, are those heat treated or you're testing them out of the machine?
Oh, those are tested right out of the machine.
Okay. And I guess the cubes that.
They're very dense, yeah.
Is there, this is the final question, those two things against this. Is there a gradient in that microstructure from the top down to the bottom where the heat has been allowed to build up?
Nothing noticeable. We didn't do any sort of detailed characterization of taking dedicated hardness measurements or profiles. We did a few cross sections, and it was, I would say, the variation section to section was about the same as you got top to bottom. Because I think a large part of that is because we didn't drastically modify the process from what the company has developed, which is, they've worked a lot on it to modify it. We modified it just as needed to make it work with the CMPs. So no, we don't really see much of that. Future work, we actually do want to deliberately grade the structures, even pure structures, but actually introduce nanoparticles in different amounts to play with that.
I guess in the turbine blade, like in the bottom, where there's a huge thing, you see one thing, and then up in the top where you have fins that are
Yeah, actually, a lot of our motivation for working with function graded materials, which is a lot of where my future work is going, is that you need very different properties. Let's say the base of something, the structural load bearing component, as opposed to the surface. The surface is where you start dealing with wear, impact, corrosion. You need different properties there, and we can tailor properties just where it's needed.
More questions? So yeah, I have a couple of questions. So like when you do like your powder processing, right? And you kind of decorating your powder. Do you consider like frictional forces, like they were affecting flowability of the powder or something?
Within the powder processing, there's some studies that, and we kind of see it, we haven't done anything systematic, but when you have, let's say, like graphene platelets in there, they can actually serve as kind of solid state lubricant and actually reduce the actual strains imparted in them. So two main things that kind of affect our processing routine that we can't use the same formula for one system to another is the hardness of the base powder. So when we're milling aluminum, it's actually a much lower energy condition than when we mill stainless steel. The stainless steel powder essentially acts as its own milling. And then the other difference is whether we have large micro ceramic particulates that also cause indentation impact, or if we have carbon nanotubes or graphene, we notice a lot less damage. Probably because of that reason, but it's very hard to characterize. But those are lubricious spaces that can give you essentially minimize the force of an actual impact.
And one more probably question. Do you guys have more questions? Otherwise, I'll take one more. So when you're talking about these composites, right? I'm always curious, like what would be kind of a fracture look like? Like, do you see any crack initiation sites? So I mean, I guess it's kind of follow-up question to Dr. Narayan. It's like how the interfaces look like. I mean, there could be like crack initiation sites or what or not.
So I actually consider the interface question to be a little different. In that case, you don't want to see what's going on with the fracture, but actually fracture morphology is very common because we want to see what's happening to the nanotubes. And we can get a pretty good idea if we see that they're still embedded, or if they're torn out, or if you start seeing that sliding mechanism. The sliding mechanism is actually really easy to see with graphene platelets. And then in general, if we're getting this high strength phase, we also want to make sure that we're not causing brittleness. So we can just look kind of classically as, are we getting a dimpled morphology? Are we getting any signs of striations if we're doing fatigue? So we do look at that mostly when we're doing tensile testing or even adhesion tests. We do look for signs of CNT participation, survival. We're actually trying to do that. We do have a, I actually haven't asked it that's here, but we do have a tensile test within an SEM with the objective being that we can actually see if, as we pull this, as we form a crack, do we see the participation of nanotubes, either bearing load or becoming fractured. So that's kind of, but most of the time we just do post-mortem to try to look for their presence or survival. So.
Just one, any question? If not, okay, the last one. So I'm really curious to like see, so when you're adding all these different, making composites, different additives, is there like any way you can choose like additives to say, okay, this additive would give me like kind of no fracture or, better properties or?
Yeah, that's kind of the classic question of how do we choose what we're trying to do? And that's why I really like to work with people that do modeling a little bit better to try to get a more systematic kind of selection of our materials. A lot of what we do right now is we try to make use of materials that are commercially available because we need to make oftentimes kilograms of these powders. So for example, we're really interested in working with boron nitride nanotubes, but for about a gram, you need $1,000 for that. So extremely unpractical. No, naval use of it or application. So nanotubes are kind of the main, carbon nanotubes are the main person there to work with. And graphene nanoplatelets have kind of recently become very cheap, and you can get them for less than $1,000 per kilogram. So a lot of it is kind of economics driven. There's all sorts of nanotubes that we could envision, and that would be something where it's useful to maybe actually simulate those properties. And then, okay, say to the people who make these, we know this nano material works. Let's try to make this commercially available. But right now we're limited a lot to carbon nanotubes in terms of kind of the composition that we can work with, at least for nanotubes.
Okay, thank you. Any more questions? Okay, if not, let's thank our speaker one more time.
All right, thank you.